Hello viewers, welcome to Senior College Mathematics. In this series of teachings, we have college geometry. Lesson 16, chord properties of a circle, part 1. Circle geometry deals with the study of size and angle of circle deductively. Deductively means that we shall be proving some properties of circle. Before we consider chord properties of a circle, let us examine a circle. Now, a circle is the set of all points at a constant, that is, equidistant from a fixed point on a plane. When you have a fixed point and you have other points moving from that fixed point to the circumference, what you have is a circle. The fixed point is the center of the circle. The distance from the fixed point to any point on the circumference is the radius of the circle. Now, this is the fixed point. From this fixed point, you have this distance. It is a radius. From this fixed point, if you have another distance, it is also a radius. The diameter of a circle is the largest chord of the circle and divides the circle into two equal parts. It is the largest chord because it passes through the center of the circle. So diameter is the largest chord. We have other chords in the circle, but the largest one which passes through the center has a special name, and it is the diameter. A diameter divides the circle into equal parts, precisely two equal parts, called semicircle. A chord divides the circle into two parts, not necessarily equal, but we have two parts. The first part, or the major segment, is the larger part of the circle, while the minor segment is the smaller part of the circle. Now, outside the major segment, you have the major arc. Outside the minor segment, you have the minor arc. You can see the chord dividing the circle into two parts, the larger parts and the smaller parts. Each of these parts is called the alternate segment of the other, and you have this as a semicircle because you have a chord that divides a circle into two equal parts, and one part, or each of the parts, is a semicircle. We shall consider the chord properties of a circle in form of theorems. So we have theorem 1. Equal chords of a circle subtend equal angles at the center of the circle. So you have this circle, O is the center. You have two chords, A, B, and C, D. Let's see what follows. Given chords A, B, and C, D of circle center O, which are equal in length, we want to prove that angle AOB this angle is equal to angle COD, this angle. Because the chords are equal, this theorem is stating that the angles they subtend are equal. Construction: join AO, BO, CO, and DO. Proof: the procedures to follow in triangles ABO and CDO above. You have it that AB is equal to CD given the two chords are equal. AO is equal to BO is equal to CO is equal to DO. That is radii of the same circle. Previously, I've said that the distance from the center of the circle to any point on the circumference, they are all equal. That is why AO is equal to BO is equal to CO and is equal to DO. Because this is true, you have it that triangles ABO and CDO are congruent triangles. What is the reason? All sides are equal. That is S, S, and S. Because of these reasons, we have it that angle AOB is equal to angle COD. Theorem 2. Equal chords of the same circle subtend equal angles at the circumference of the circle. So this is the angle at circumference. This is the angle at circumference. This theorem is stating that if the chords are equal, the angle they subtend at the circumference are also equal. Given a circle center O with two chords AB and CD, to prove angle ASB, that is, this angle is equal to angle CYD, that is this angle. Construction: join AO, BO, CO, and DO. Proof: obtuse angle AOB is equal to obtuse angle COD. This is what we proved in theorem 1. Now, if we are considering ABO, this angle is obtuse, and in triangle COD, this angle is obtuse, and both are equal from theorem 1. Equal chords subtend equal angles at the center. Equal chords subtend equal angles at the center. Now we have it that reflex angle AOB, that is considering triangle AOB. In that triangle, we have two angles there. The reflex angle, this is the triangle now. So this outer angle is reflex, plus the obtuse angle AOB, the sum is equal to 360 degrees angles at a point. From here, if you make the reflex angle the subject, you have to transfer this to the right hand side and you have it in this form. If you do the same thing considering triangle COD, you have it that its reflex angle is also 360 degrees minus the obtuse angle. It follows that S is equal to y is equal to 1 over 2 AOB. So here is small letter s and here is small letter y. Now this is the angle at center. From here you should know that angle at center is twice angle at circumference. So you have angle at center is equal to 2s is equal to 2y. If you make s and y the subject, you have it in this form. When we come to circle theorems, we are going to look at this very well. Now look at s. S is the angle represented by ASB and y is represented by CYD, and both angles are equal. Theorem 3. Equal chords of equal circles subtend equal angles at the circumference of the circles. We have two circles, A, B, C, P, Q, arrow with center O respectively. So the angle at the circumference, they are equal. From the figures above, angle ABC, this angle is equal to 1 over 2 angle AOC. The reason is that angle at center is equal to 2 times angle at circumference. Now in the second figure, you have it that angle PQ arrow, this angle is equal to 1 over 2 angle PO arrow. Same reason. Now this is what happened. Actually, we're supposed to have angle AOC equal to 2 times angle ABC. If you make ABC the subject by dividing through by 2, you have this outcome. The same thing you have here. Since we have both sides to be equal, the right hand side, it follows that angle ABC is equal to angle PQ arrow. We have perpendicular bisectors of chords. In that, we shall consider theorem 4. The perpendicular line drawn from the center of a circle to a chord bisects the chord at right angle. So here you have PQ as a chord, you have OM as the perpendicular line drawn from the center of the circle. At the point of intersection with the chord, the angle formed is 90 degrees, a right angle. Given a chord PQ of a circle center O, you have OM is perpendicular to PQ, and we want to prove that PM is equal to QM. Construction: join O to P and Q, that is OP then OQ. Both are radii. Proof: considering triangles POM and QOM, you have it that OP is equal to OQ, that is equal radii. You have angle PMO is equal to angle QMO. Given OM is common, Now angle OMP is equal to angle OMQ, and that is 90 degrees. It is also given. It follows that triangle POM is equal to triangle QOM. You have two sides and an included angle. For that reason, PM is equal to QM. Theorem 5. A straight line drawn from the center of a circle which bisects a chord of a circle which is not a diameter is perpendicular to the chord. Given a circle whose center is O, we have chords PQ and OM such that PM is equal to QM. We proved this in Theorem 4. Here, we want to prove that angle PMO is equal to QMO. One rectangle construction. Join O to P and Q, that is OP, and you have OQ. Both are radii. Proof. OP is equal to OQ, equal radii. You have PM equal to QM. That is given in the diagram. OM is common. It follows that angle OPM is equal to OMQ, and that is 90 degrees. These two angles you have here, they are 90 degrees respectively. Therefore, triangle PMO is equal to triangle QMO, equal sides. But if you add the two angles, angle PMO plus QMO, the sum is equal to 180 degrees. Sum of angles on a straight line, but two angles are equal. Therefore means that we can replace this with PMO, or you replace this with QMO. Whichever way, when you add, you have it in this form. Divide through by 2, and you have angle PMO to be equal to 90 degrees. Thus, angle PMO that is equal to angle QMO, both angles are equal to 90 degrees respectively. Note number 1, the perpendicular bisector of a chord passes through the center of the circle. Number 2, if the chord is not a diameter, the line joining the center of the midpoint of the chord is the perpendicular bisector of the chord. If the chord is a diameter, its midpoint is the center of the circle. These are points to note. End of lesson 16. Thanks for watching and learning. Don't forget, watch out for more from the voice of Peter Kos. Lastly, if you are not safe, your life is in trouble, your life is in crisis. To avoid all of that, you have to give your life to the Lord Jesus Christ and confess Him as your Lord and personal Savior every day of your life. If you are saved already, congratulations. Live righteously and be prepared, because on the last day, some will be taken and some will be left. Take good care of yourself. Stay out of trouble. Study your books. Do the needful at all times. Flee every appearance of evil. Don't defraud others to make money. Find something good and genuine to do with your hands and your brain, and the Lord will bless you. Goodbye and stay tuned.